Good morning and thank you for being here. Now, if you remember, I was talking about the particle in a one dimensional box. We solved the Schrodinger equation for the particle. We found the so called stationary states, which as I mentioned were just the standing wave patterns that you would expect in a one dimensional system. And let me just write the wave functions and the allowed energy levels. We found that the wave functions were given by these were the wave functions if x was between 0 and L, and the wave function would be equal to 0 if x is outside, and these functions had an energy and n could take the values 1, 2, 3, etc. And if you remember, n equal to 0 is not allowed, because then the wave function would identically vanish everywhere. And further, this function will give me a total wave function. When I say total wave function, it is a function of x as well as t, which as we have seen would be given by psi n of x into e to the power of minus I E n t by h cross. That is what it is. Okay. So, this is the time dependent wave function for the stationary state, and it is given by such an expression. Each value of n will give me a different possible stationary state characterized by a different function capital psi. And what about this capital psi? It obeys this equation I h cross dou psi by dou t is equal to h psi. Or maybe I will write this equation in a slightly different fashion. I will take this to the left hand side, so that I shall get a negative sign, and the answer must be equal to 0, right. So, any psi that you have of this form, maybe I can put a subscript n here, because I itself now depends upon n, okay, and that psi n will actually obey this equation, correct. That is how it is. It does not matter what the value of n is, it will always obey that equation. And maybe I can even write it in a slightly better form by removing this psi n outside. So, I will have I h cross dou by dou t minus h operating upon psi n would be equal to 0. Let me remove that. So, these are the equations that we have. I will also represent the allowed energy levels of the system. This is my box. Extending from 0 to L. And along this axis, actually we are going to represent energy, and if you are thinking of potential energy, remember why we drew a picture like this. See, in this region the potential energy is infinity, in that region also potential energy is infinity, while inside the box the potential energy is 0. and then we look at the allowed energy levels. You can put n equal to 1, n equal to 0 is not possible, as I said. You can put n equal to 1, what is going to happen is you are going to get an energy which may be somewhere here, pi square h cross square divided by 2 ml square. You can represent that in this picture, maybe the energy is so much. Well, maybe I should write it a little bit lower. Okay. Now notice that the energy, this is actually the state that has the lowest energy, but its energy is not 0. Now if you are thinking about the system classically, suppose I had a classical particle which is trapped in a box, then what can happen is that the particle can be just sitting inside the box without moving. I mean, I have a particle which is just inside the box without moving, so it will be sitting somewhere. It has absolutely no kinetic energy because it is not moving, right, and the potential energy inside the box is 0. So therefore the total energy classically can be 0. So the particle may be just sitting here like that if it was obeying classical mechanics, and then it can have an energy 0, or in fact it may be moving, right. So suppose it is moving, it is going in this direction, then it will hit the wall and be reflected, and I can give it any energy I like. So therefore classically speaking, the particle can have any energy starting from 0 to any large value, right. But that is not possible in quantum mechanics. What is happening is that in quantum mechanics, first of all, you find that the energy cannot be 0. Right. Not only that, the energy can have only certain values. So we say that only certain discrete energy levels are possible for the particle. Okay. So these stationary states have only certain discrete values for their energies. And what are they? The lowest possible one we have found is so much, pi square h cross square by 2 ml square, and I mean you can actually ask, why is it that the particle cannot simply be sitting at one location? Why isn't that this is possible in quantum mechanics? The answer is actually quite simple. Imagine you have a particle just sitting at a particular location, then I know where exactly the particle is, therefore its uncertainty in position will be 0, because if it is sitting somewhere precisely, then uncertainty in position will be 0, and if it is not moving, it has no momentum. So it essentially means that momentum is 0. So therefore there is no uncertainty in position and there is no uncertainty in momentum, and delta x is 0, delta p also is 0, which means that I would have a situation where the uncertainty principle would be violated, right. That is the reason why energy equal to 0 is not possible for this particle which is confined within a box, because it would simply violate the uncertainty principle. So the lowest possible energy level for the particle is this one. The next one is how much? You put n equal to 2, so you are going to get an energy which may be somewhere here. That will be 4 pi square h cross square by 2 ml square. Okay. So this has n equal to, let me write the value of n here, this is n equal to 1, this is n equal to 2, and then you will have n equal to 3 somewhere here. Notice the way I draw this picture. This is the next allowed energy level, its value will be 9 pi square h cross square upon 2 ml square. And notice you see this gap is only pi square h cross square by 2 ml square, while that gap, right, it will be 4 minus 1, right. Here you have a 4, there you can say there is a 1. So, this gap is actually 3 times that gap, and that is important to notice. While if you think of this gap, how much will it be? It will be 9 minus 4, it is actually going to be 5 times pi square h cross square by 2 ml square, and this will go on happening. If you looked at the next level, actually maybe I can just draw it here, but it may not be accurate actually the spacing. I mean, it is difficult for me to show it now, but you know that that spacing is going to be how much? This is n equal to 4, it would have an energy of 16 pi square h cross square by 2 ml square, and this gap will be how much? It is going to be 7 times pi square h cross square divided by 2 ml square. So, therefore, this is another interesting thing, the spacing between successive energy levels actually increase as you go up. Okay. And further what I will do is, I will also represent the wave functions in the same picture, so that whatever we have learned is there in this picture. So, the wave functions, the way I am going to draw them is represented here. As far as this function is concerned, that will be the wave function. It is 0 there, it is 0 there, and the maximum value is right in the middle. The next state I will represent with a different color. The wave function will be looking like this. It has a node right in the middle, so it would look like that. Now, while the lowest one, the wave function is positive everywhere, so that there is no node, the next one has actually one node right in the middle of the box. So, there the function is 0, to this side the function is positive, while to the other side the function is negative. What about the next one? It would have 2 nodes and it would look like this. Well, the way I have drawn this figure, you see, it is not easy, it is not possible for me to draw the 4th wave function. So, I will just draw it here. The important thing is, you see, it has 3 nodes. So, let me put the nodes 1, 2, 3, these are the nodes. So, the function would look like this. So, these are my wave functions. But then let us imagine that it is sitting in the particle is sitting in the ground state, then the wave function will be square root of 2 by L sin pi x by L. This is the lowest possible state. The lowest possible state is actually referred to as the ground state of the system. The next possible one is referred to as the first excited state, second excited state, third excited state, right. And imagine that you have prepared your system. Imagine that it is in contact. I mean, my system is a particle, but imagine that it is interacting with the surroundings, and the surroundings is at a temperature of T, right, maybe at room temperature. Then what will happen is that, I mean, I suppose you know a little bit about this. You will have a Boltzmann distribution of the particle, right. When the particle may be in this state, or maybe in that state, or maybe in that state, with what is referred to as a Boltzmann distribution. which will depend exponentially upon the allowed the energy of the particle. But suppose your surroundings is at 0 Kelvin, which is an idealized situation. If the surroundings is at 0 Kelvin, what will happen is that your particle will be in the lowest possible state, right. But even in that lowest possible state, the particle has an energy. So, even if the system is at 0, even if the surroundings are at 0 Kelvin, even when it is in the lowest possible state, the system has an energy, and therefore, this energy that is possessed by the particle even at 0 Kelvin is referred to as 0 point energy. Where do I write it? Maybe here, 0 point energy. Why do you say that this is the 0 point energy? Because even in the lowest possible state, the system has a non-zero energy, and that is why you say it is 0 point energy. I mean at absolute 0. If the system obeyed actually classical mechanics, what will happen is that it will not do anything, it will not move, it will be just sitting there and the energy would be actually 0. But quantum mechanics does not allow that, right, and that even at absolute 0 the system would have that much energy, and we have seen the reason for this. The reason is simply your uncertainty principle. If the particle just sat there without moving, that will violate the uncertainty principle. So, it has to be moving. Okay. Now, let us look at this particular function. This is the function that we refer to as psi 1 of x. Remember, this is only the time independent part, that means it is only the position dependent part of the wave function. And the function has this form. In fact, yesterday I had drawn the value of psi 1 square, how it will look like, and the maximum or the most probable position. I showed that it is at the middle of the box. But now suppose I can do some experiment where I will measure the position of the particle, right. Then what do you find? Most of the time you will find that the particle is right in the middle, but then of course other positions are also probable, and therefore what will happen is that when I do the experiment, remember our postulate number 3, each time you may get a different answer, and suppose I make an average of all these measurements, what would be the answer? As you remember, the average of a large number of measurements would be given by the expectation value of x, which I can calculate from a knowledge of the wave function. How would I calculate that? Well, actually the way I would have to calculate is I would have to have the operator associated with position, which is just x itself. I will have to allow that to operate upon, in principle I should say psi 1 xt and psi 1 star xt, and then multiplied by dx, integrate from minus infinity to plus infinity, and divide this by integral minus infinity to plus infinity dx psi 1 x t star psi 1 x t dx. This is our very detailed expression, but you would realize from our discussion yesterday that there is a time dependence here, there is a time dependence there, but stationary states are such that the time dependence from here will be exactly cancelled by the time dependence from there. And what happens is that this psi 1 is not really necessary to use that capital psi 1, but it is enough if you just use this psi 1, right. So, let us do that. Let me make that simplification, remove this with psi 1 of x and that with psi 1 star of x, because there is time dependence, but that time dependence gets exactly cancelled. Time dependence of one is cancelled by the time dependence of the other, that is what we saw yesterday. And not only that, it is not necessary to integrate from minus infinity to plus infinity, but it is enough if you integrate from 0 to L, because it is only in that region that psi 1 of x is non-zero. And you can do the same kind of thing below, down here. You can say, well, you would have psi 1 star of x and psi 1 of x, okay. And again you do not need to integrate from 0 to minus infinity to plus infinity, but it is enough if you integrate from 0 to L and to do this. But then of course, the way we have taken this function, remember we did calculate this, and how did we calculate that? We arrived at this expression, the square root of 2 by L, by using the normalization condition, by imposing the condition that this integral when you evaluate it, the answer is 1. That is how this square root of 2 by L was done. Therefore, if I am using that function, actually this integral I do not have to perform, because I already know what its answer is, it is 1. So, this is the object that you have to evaluate, and even here you can make simplifications, because if you look at psi 1, there is no effect of star operation, taking the complex conjugate does not affect it, because it does not contain square root of minus 1. So, even that can be removed, and therefore, effectively what is it that I have after all these simplifications? What I have is integral dx of psi 1 of x is actually occurring 2 times, so psi 1 square x into x is the integral that I have. I mean, I can of course calculate this, I will do that, but let us just think about the problem physically. I have a particle which I know is somewhere between x is equal to 0 and x is equal to L, okay. And further, if I look at the most probable position, which is this point L by 2, right. If you look at the wave function, you will find that this wave function is actually symmetric about that point, and if you look at the square of the wave function, you will find that even the square of the wave function is symmetric about that point, which means that when I make a measurement, right, it may be to the particle may be found to the left of this point or to the right of the point with equal chance, and therefore, what would you expect the average to be? Obviously, the average has to be equal to L by 2, right, because the particle may be to the left of that point or maybe to the right of that point with equal likelihood, and therefore, even without doing this calculation, I can make a prediction, I can make the prediction that it has to be equal to L by 2, okay. And this is exactly what happens. I will not do the complete integral, because the integrals are not that difficult, but I will tell you how it comes around. If you integrate from 0, I mean the integral that you have to perform is integral 0 to L dx sin square pi x divided by L into x. So, here you say you have sin square, but there is a trigonometric identity that you can use. Sin square theta is actually equal to 1 minus cos 2 theta divided by 2. So, you can use this trigonometric identity. So, instead of that sin square pi x by L, you can actually write sin square pi x by L may be written as 1 minus cos 2 pi x by L divided by 2, okay. Now, what you can do is you can substitute that in here, then you will see that there are 2 terms, correct. there are two terms in the integral. What happens is that the first term is non-zero, while if you evaluated the second term, you will find that the second term is identically equal to 0. And the first term, so let me just look at the first term. What is the first term? Integral 0 to L dx. The first term is simply, well, I did make a mistake, didn't I? At this point I did make a mistake, because psi 1 of x actually contains, where is it, square root of 2 by L. I didn't write this square root of t by L, I just wrote the sine square term. So therefore I have to correct for that mistake. There will be a 2 by L sitting here. Correct? So therefore I should have written that I would have 2 by L, and then I would of course have this sine square, which is actually going to give me 1 minus cos 2 pi x by L divided by 2 into x. So that is what the integral is, but then obviously as I told you, there are two terms. The first term will come from here, the second term will come from there, but that second term I am not actually going to evaluate, other than tell you that if you did evaluate the contribution from that term, it is going to be 0. Maybe you can do this as an exercise, and then what will happen to the other term? I will get 2 by L integral 0 to L dx into x is what you are going to get from the first term, and there is a half there. And this is a pretty straightforward integral. Okay. What will happen is that you will get 2 by L into L square by 2, as there is as a result of doing the integral, and there is a half already there. So therefore this is what will happen. And if you cancelled all these things properly, what is the answer? The answer is going to be L by 2. Okay, which is what I would have expected physically anyway. Now interestingly, you say I have done this calculation for the lowest possible stage, but I can do the calculation for any stage. But do I need to do this calculation? You can use your physical argument, right? Where whatever be the state, you take psi n square of x, you will find that it is symmetric around the middle point, and therefore it does not really matter what the state is. What I would expect is that the average value of the position should be L by 2, and that you can easily calculate and show, but it is not necessary, because my physical intuition tells me that it has to be equal to L by 2, because simply because it does not matter what the value of n is, psi n square is going to be symmetric about the middle point of the box. So having completed that calculation, let me look at the expectation value of momentum. The particle is moving only in one direction, so any momentum that I would like to think of would be denoted as Px. So if you wanted to calculate the expectation value of Px, actually to be very precise, I should say the operator associated with momentum, right, that is the expectation value. What is it that I am trying to calculate? The particle is within the box, I want to calculate the average value of momentum. If I can make a large number of measurements of momentum, I take its average. What would be the answer? The answer is going to be this with, of course, Px occurring there. So what is actually Px? Well, actually I should start from the beginning, where I would start with the time dependent wave function, and did exactly what I had done earlier, but because we have already done it in the case of position, I am not going to do that. The expression is going to be extremely simple, because you will have this the same kind of simplifications as earlier. So, the operator is actually minus IH cross dou by dou x, that is the momentum operator, and it is going to operate upon psi 1 of x. So, that is the object that I have to evaluate, but then again, I mean, we can think about it physically. You see, the box is here, let me say, the particle is inside. What is going to happen physically? The particle will be, maybe it is moving in this direction at one instant, but then of course it has to hit the wall. That is the physical way to think about it, and then reflect. So, therefore, the particle may be moving in this direction or may be moving in the opposite direction with equal likelihood, right. If it is moving in this direction, you would expect momentum is 0, while if it is moving in the opposite direction, you would expect that, sorry, I made another mistake. Point out my mistakes to me. If the particle is moving in this direction, its momentum will be positive, while if it is moving in the opposite direction, the momentum will be negative. So, what do you expect on an average to happen? The answer is it has to be 0. So, without doing any calculation, I could have said that the answer has to be 0, but here this integral is actually fairly easy. See, this minus IH cross I can take out. I would have integral 0 to L dx psi 1 of x, then I have dou by dou x operating upon psi 1 of x, but that is nothing but the derivative of psi 1 of x with respect to x, correct. That is what it is. And what would that be? Well, it is actually minus IH cross. Well, you have psi 1 of x multiplied by the derivative of psi 1 of x, very easy to do this integral. It is nothing but, the integral is nothing but psi 1 of x square divided by 2, right, because the derivative of this is nothing but psi 1 of x into d psi 1 by dx, right. This integral is nothing but 1 by 2 psi 1 of x square, but then you have to substitute the limits. Limits are from 0 to L. But you have the nice thing, when x is equal to 0, psi 1, I know it must be 0, and when x is equal to L, psi 1 again must be 0. So, therefore, at the boundaries, these are the boundaries, at the boundaries the function is 0. So, the boundaries psi 1 of x is 0. So, therefore, you get the entire answer to be 0. And you would realize that it does not matter whether it is the lowest possible state or the first excited state, you can have any value for the quantum number n, same derivation can be done, and you will find that for all the states the average value of the momentum has to be 0. But what about, I mean, that is all fine, but what about, suppose I am going to think of the square of the momentum, right. Well, momentum may be positive or negative, but the square is guaranteed to be positive. So, if I was going to calculate the average of the square of the momentum, let me just modify what is written here, px square. Let me remove the other parts. So, I want to calculate px square. How can I do that? You will have to put a px square here, and what is going to happen is you will get integral 0 to L dx psi 1 of x square of px. I know it is just minus h cross square dou square upon dou x square psi 1 of x. Remember our discussion of the postulates, in which we did calculate the square, the operator corresponding to the square of momentum, and it is just h cross square minus h cross square by 2, sorry, minus h cross square dou square upon dou x square, that is what it is. But then what is going to happen is I am going to substitute for psi 1, I will get as 2 by L integral 0 to L dx sin pi x by L dou square upon dou x square sin pi x by L So, you have to take the second derivative of the sine function. If you remember how to calculate derivatives, the first time you differentiate a sine, you will get a cosine, and the next time you differentiate, you are going to get the sine back. So, dou square upon dou x square operating upon sine, what will it give me? Let me continue from here on to here, or maybe somewhere up. It will be equal to 2 by L integral 0 to L dx sin pi x by L. When you carry two differentiations, the answer is going to be minus pi by L the whole square, because each time you differentiate, a factor of pi by L is going to come out. So, you are going to get minus pi by L square sin pi x by L. And this object is just a constant. So, okay, again another mistake, I mean please point out when I make mistakes, this negative sign should have been, I have forgotten to write h cross square, also I have forgotten to write, this keeps on happening to me. So, that means I shall have to modify my equations. This minus h cross square I will have to put it outside, because I should not forget that, right, which means that I shall have to put a minus h cross square here also. So, therefore, what is going to happen, this factor and that factor I can combine, what would I get, h cross square, there is a negative sign there and the negative sign there, I can forget the two negative signs, h cross square pi square divided by L square is what you are going to get, and then you will have of course this 2 by L, and you are going to get integral 0 to L dx sin pi by x, another sin pi by x. So, you will get sin square pi x by L, right. This is what you are going to get, and if you look at this integral is nothing but psi 1 square of x dx integral 0 to L. Right, this whole thing you can say it is just psi 1 of x square dx, and what is that? Your function, remember, is normalized, and therefore, that integral you do not have to actually perform, because you know what it is equal to 1, and hence this is equal to 1, and therefore, this object which actually is equal to this integral that we were trying to evaluate, this object is nothing but h cross square pi square by L square. So, we have evaluated the expectation value of p x square, average value of the square of the momentum. Now, I have done it for the ground state n equal to 1, but suppose I had done it for a general state with an arbitrary n, what would you expect? The thing that is going to happen is that you will have an n pi here, and an n pi is going to occur everywhere, But then when you carry out the differentiation with respect to x, you see in this case it is a pi by x that is coming out. But if I had sin n pi x by L, then what will happen, and n pi will come out, right. Each differentiation one n pi will come out. So, therefore, if the final answer in such a situation would be not just pi square h cross square by L square, but n square pi square h cross square by L square. So, for a general state, what would be the value of px square average? It would be simply n square pi square h cross square by L square. Now, it is simply straightforward to calculate average value of kinetic energy, right. What is kinetic energy operator? It is going to be px square divided by 2m. This is the kinetic energy operator. So, if you wanted to calculate the average value of this, what will happen? Well, you see 1 by 2m is just a constant. So, you will have the average value of px square by 2m, and we have already calculated average value of px square. It is going to be n square pi square h cross square divided by 2m L square. Right. If you calculated the average value of kinetic energy in the nth state, this is going to be the answer. And what is this actually? If you look at this expression, this is nothing but the expression for the energy level. So, if you just calculate the average value of kinetic energy, you are getting the total energy of the system. Is that surprising? No, it is not, because the particle has 0 potential energy. So, there is no contribution from the potential energy, the energy is purely kinetic. That is why this happens. Okay. Now, I want to illustrate a simple chemical application of this model. Let us think of butadiene, one 3-butadiene to be precise. This is the molecule. It has 2 conjugated carbon-carbon double bonds, and if you do experiments, you can measure this distance using X-ray techniques. This bond length is 1.38, this is 1.38, and that bond length is 1.48. So, that the distance between the 2 end carbon atoms, how much would it be? You can sum all these things. So, 2.76 plus 1.48, you will find that it is 4.24 angstroms. Well, I wonder whether I mentioned the units, these are in angstroms. So, how much is an angstrom? An angstrom is, again let me remind your memory, it is 10 to the power of minus 8 centimeters, or it is equal to 10 to the power of minus 10 meters. Now, butadiene has 4 carbon atoms. Remember my discussion yesterday, I said that each carbon is sp2 hybridized. This will leave a p orbital perpendicular to the plane of the molecule, and so there are 4 p orbitals which are unhybridized, one sitting on each carbon, and these 4 p orbitals can overlap right. And if you put an electron into this pi system, this system is referred to as the pi system of the molecule. If you put an electron into the pi system, the electron can be thought of as moving from one end of the molecule to the other end, and this model you can try to apply to the system. So, what is it? You think of any particular electron in the pi system, it is moving from one end of the molecule to the other end of the molecule, and what would you expect? You would expect that the length of the box is perhaps something like 4.24 roughly. I mean, it is of the order of 4 or maybe 5 angstroms typically. So, therefore, I say I have a box which is of length. I mean, let me not worry about this number that is given. Let me try to estimate the length using experiments. So, I say that I have a box which is of length L, and if you think of these electrons which are confined to that length L, their allowed energy levels are given here. This is the first allowed energy level, this is the second, that is the third, and so on. But remember, each carbon atom will contribute only one electron to the pi system, right. The other electrons of each carbon is used to form sigma bonds with the hydrogens and with the other carbon. So, therefore, how many pi electrons should I worry about? Because there are 4 carbon atoms, there are 4 pi electrons. And how are they going to set? Well, these are the allowed energy levels. So, out of these 4 pi electrons, 2 of them will sit here in this energy level, right. Well, I am anticipating your previous knowledge, right. You would have some previous knowledge. So, therefore, only 2 electrons can be sitting in any one particular state. So, these are 2 electrons there, and you have 2 electrons sitting here, and that is all. There are 4 electrons, all of them are accounted for. The first 2 are sitting in the lowest possible state, the second 2 electrons, second set is sitting in the next state. So, that is what you would expect to happen in the molecule. The pi electrons are accommodated in the first and the second allowed energy levels. Just remember, we are thinking only of the pi electrons, we are not worried about the sigma electrons which form the framework of the molecule. And now, suppose I take this molecule and allow it to interact with electromagnetic radiation. As I was mentioning to you, it is possible for electromagnetic radiation to make the potential energy time dependent, and as a result of that, it is possible for the wave function to get modified, and effectively what would happen is that light quanta may be absorbed, as a result of which one electron from here may be promoted from that orbit, from that state to this state. Okay. So, one electron could be promoted from here to there, and you can see how much energy will be required to cause this promotion. Energy of the initial state, as far as that electron is concerned, it was having an energy which is equal to so much, and as a result of the absorption of radiation, it has gone on to that state. So, therefore, the change in energy, which I will denote as delta E, in this case will be actually the energy of the state with n equal to 3 minus the energy of the state with n equal to 2, right. That is the change in energy, and that will be equal to 5 pi square h cross square divided by 2 m L square, right, and that should be equal to the change in energy. And if this is brought about by a photon of frequency nu, then h nu has to be equal to the change in energy, and that must be equal to so much. And so, it is possible for you to calculate nu. and it is possible for you to estimate nu or not estimate, you can determine nu by studying the absorption of the molecule. You can find out at what frequency the radiation is absorbed, what is the frequency of the radiation that is absorbed by the molecule. Experimentally you can determine that and then use that. I think I will stop here. Thank you for listening.